Okay. So now we are moving towards the very last topic of our course on theory of probability. In the last topic, we're gonna basically talk about the strong law of large numbers. What is the meaning of the strong law of large numbers, its interpretation, and its detailed proof actually. So I'll prove this strong law of large numbers in detail. We also did one law of large numbers basically, which was what you call the weak law of large numbers actually. Obviously this kind of arises a natural question that why the strong law of large number is strong and the weak law of large number is weak actually. Okay, and what are the delicate difference between them? So I would like to talk about their differences, okay, their interpretations and their differences. What essentially both law of large numbers says is that if you have, for example, a population, okay, and you have an average of that population actually, okay. Now out of that population, if you choose a sample and compute the average of that sample, okay, and you keep on making your sample bigger and bigger and bigger, you will see that your sample average will get closer and closer and closer to the population average, okay, as your sample size increases. So what does simply both laws are saying in some manner is that the average of the sample size will get closer to the average of the population, okay, as n gets bigger and bigger and bigger actually. I'll talk about it through specific examples, making so that we can really make sense of this statement, because it is delicate actually. So people can sometimes know the proof, but they really don't understand the difference between both actually. Anyway, so imagine I have a sequence of IIDs, okay. So I have a population of the random variables actually, okay. So I have population of random variables in which in this population every individual member of the population in each random variable is independent and it's identically distributed. They all follow the same distribution and they all have a common mean actually. You can call it, this is the actual average mean of the population actually. Okay, so if you have population and you are, for example, talking about the weight of the population, then mu is the average weight of the entire population actually. Okay, population with a common average with an actual average mu actually. Then what does weak law of large number is saying? That for any given epsilon positive, okay, so epsilon could be any numbers between what do you call it could be a really small number but a positive number. You can choose it any number you want, okay. So for a chosen epsilon number, however small or big it is, the difference between the sample average actually. So out of this population, I took, for example, n elements, n what do you call random variables or n observations or n weights actually, okay, and I computed the sample average of that what do you call n random variables. This sample average, the difference between this sample average and the average of the population will be greater than or equal to 0. Will be greater than or equal to this really small number. I'm asking, what are the chances of happening it? Okay, what are the chances of happening it? The weak law of large numbers says that the probability that your sample average will be different from actual average by a number, say epsilon, or at least by a number epsilon, probability of happening this is nearly zero. As you increase the sample size, the more sample size you increase, the sample average will get closer and closer and closer to what do you call closer and closer and closer to the population average. Okay? In other words, the difference, chances that the difference between the sample average and the population average is bigger than a really small number, chances of happening of this event is equal to zero. Okay? Chances of happening of this event is equal to zero. As you increase the sample size, the more bigger sample you're going to have out of population and compute its average, the more this sample average will get closer to what do you call the actual population average actually. Okay. So this statement. Okay. So let's not a little bit talk about it actually. So let's move to, for example, the strong law of large numbers and see that what does it says. So in the strong law of large numbers, you have the precisely same assumptions actually. Okay, the precisely same assumptions that you have a population of random variables, population of random quantities which are independent and identically distributed. They all follow the same distribution with a finite mean mu. Okay. Then this says that as the sample size of the average, okay, as you take a bigger and bigger sample out of this population and compute its average, this average will converge to what do you call the actual population average. It will converge to the population average as your sample size gets bigger and bigger and bigger. And this event will happen with the probability 1. With the probability 1 actually. So, sample average will converge to population average as my sample size gets bigger and bigger and bigger. And this event will happen with the probability, what do you call, 1 actually. Now if I rewrite this statement in a bit different manner, if I rewrite this statement or rewrite, say, I take the complement of this statement, okay, so take the complement of this statement. What would be the complementary statement of this? The complementary statement of this is going to be the limit n goes to infinity, probability that the difference between the sample average and the population average is going to be smaller than or equal to my chosen number, or maybe less than epsilon, their difference is going to be smaller than my chosen epsilon, and you can choose this epsilon to be as much as, you know, what do you call, small, is equal to 1. Is equal to 1. Okay? So see this statement and see this statement actually. What is the difference? So one thing that you can immediately observe, that in this statement the limit is inside, while in this statement the limit is outside actually. But what does it mean? What does it mean? So here is what do you call the crucial difference between both actually. So the crucial difference is that this statement is talking about a sequence of probabilities. So if I, for example, give this probability a name, say a sequence Pn, then this statement says that the limit of the sequence of the probabilities, that the difference of the sample average and the population average is going to be bigger than or equal to what you call a really small number. So this sequence of probabilities converges to 0 actually. Okay, and these sequence of probabilities converges to what do you call 1, which is equivalent to both actually, which is equivalent to both. So here in this statement, okay, in this statement you are saying that the sequence of probabilities of happening of this event goes to 0. In other words, as my sample size will get bigger and bigger and bigger, chances of happening of this event are going to converge to 0. Okay, are going to converge to 0. So here the chances are going to the 0, not the average. Okay, not the average. That the chances, okay, the chances, the sequence of probabilities, for example, let's call this Qn, the sequence of the probabilities that the sample average will converge to actual average is 1 actually. So in other words, this sequence of probabilities converges to 1. So here the chances are converging. Okay, like these two guys may or may not converge. Okay, that's a subtle difference between both actually. Now if you come to here, okay, if you come to this statement, what does this say? This statement says that as the sample size increases, the actual average, the sample average will converge to the actual average. So the average is converging to the actual average, and happening of this event has 1 probability, so the probability 1 actually. Okay, so we call such convergence as we will, when we will do our course on stochastic calculus, actually we're gonna do the major parts of the probability theory again, but we're gonna do them in a measure theoretic way. Okay, so we're gonna use measure theory to describe them actually. Then we will talk in more detail about that. Okay, what is the more rigorous and mathematical difference between both? This is called the almost sure convergence actually. Okay, this is called almost sure convergence. Okay, so in other words, the sample mean converges to the population mean almost surely. And this kind of convergence, where the sequence of the probabilities of happening of an event converges to 0, or they converge to some number, you call this as the convergence in probability. You call this convergence in probability. Okay, and why this result is strong and this is what do you call weak? Because almost sure convergence implies convergence in probability. Okay, almost sure convergence implies convergence in probability. In other words, if this result is true, then this is true as well actually. Okay, So the strong law of large numbers really is a more generic case actually, while the weak law of large numbers is a subtle case. Let me try to explain this to you with an example. Okay. By the way, the frequency definition actually, okay, the definition that, for example, we usually use for example, that okay, you roll a die, the probability of happening of say showing up of say 6 is 1/6 actually. Showing up of 1 is 1/6. Okay, so this 1/6 is like the frequency probability. So what is the justification of that? The justification of that is basically comes from the law of large numbers. So why we rely on these probabilities, that the probability of head is 1/2 and probability of tail is also 1/2, why we take them as say 1/2 and 1/2? Okay, we take them as 1/2 and 1/2 because of the law of large numbers actually, because there is a theoretical justification behind them. Okay, so let me try to give you a subtle difference between both. Okay, a subtle difference between both. For example, let's take any example actually. So for example, let's observe that a baby is born in a family. Okay, so you have family. Okay, so imagine a baby is born. Okay, not being prejudiced, but imagine a baby is born. Then what are the chances that the baby that has born or that will born is boy, and what are the chances that the baby that will born is going to be girl? So usually we take them as what do you call that the probability of baby born boy is what do you call 1/2, and the probability that a girl will born is 1/2 actually. You call these probabilities as the theoretical probabilities actually. Okay, we call them, these are the theoretical probabilities. Okay, but how we came to these theoretical probability, how we came to this conclusion that that when you're gonna, for example, toss a coin, there is one half chance that head will occur and 1/2 chance that tail will occur. There is 1/2 chance that boy will born and there is 1/2 chance that girl will born. So these 1/2s are the theoretical probabilities. So for example, now you went to you observed some families. So imagine you observed 10 families. Okay, you observed 10 families, and it turns out that out of 10 families, okay, 5 families. So let's focus on, for example, probability of girl being born is 1/2. Okay, so you observe that, for example, 10 families, and it turns out that there were 4 boys born and 6 girls were born actually. Okay, 6 girls were born. So what would be this probability? So what do you call the observed probability for us actually? So it should be like, okay, 6 by 10, in other words 0.6 actually. So if you make 10 observations, okay, it turns out that the observed probability is 0.6 actually. Okay. For example, now you observe say 100 families now. Okay, and it turns out that there are say 51 boys and 49 girls actually. Okay, so what is now the observed probability of girls being born, or what is the frequency of the, what do you call, girls born out of 100. So this frequency or the observed probability is 49 by 100. So in other words, you're going to get 0.49. How about instead of 100, you did say 1,000 actually. What do you call observations? And it turns out that out of 1,000, say 503 are boys and 497 are girls actually. So what would be observed probability or frequency in this case? So 0.497. Okay, and say you. So what is happening? I mean, if you see this pattern of the probabilities, okay, if you see this pattern of the probabilities, what does the law of large number is saying to you? That as you increase the sample size, this pattern of the probabilities, this sequence of the probabilities will converge to 1/2. This will converge to 1/2. You'll get more closer and closer and closer to 1/2. Okay, so these are some fictitious numbers, but that's what really illustrate what really the first, it's a weak law of large number is saying actually, that the sequence of probabilities, okay, will converge to what do you call a theoretical probability. Okay, the sequence of probability will converge to a theoretical probability. So that's what could be, you can treat it as one interpretation actually. Okay. Now, so I hope that you see that you know why we are treating 1/2 as a probability of, say, you know, girl being born, or probability that head appears. Okay, so why we are taking it to be 1/2? Because if you repeat this experiment again and again and again, the probabilities or the frequencies are going to converge to 1/2 actually. They are going to always converge to 1/2. That would be one of the interpretation of law of large numbers actually. What could be the other interpretation, for example? That, okay, you go out to, say, you know, Sukkur University, okay, and your task is to talk about, let's try to make sense of this through another way actually, okay. Consider you go to the Sukkur University, okay, and you want to say know that what is the average height of the people, okay, in Sukkur University actually, okay, what is the average height of the students in Sukkur University, okay. So imagine, okay, the administration knows that the average height of, or we know, someone knows that the average height of the people in students in Sukkur University is say 5 feet actually, okay, 5 feet, 5 feet and 5 inches, something like that, 5 feet, 5 inches actually, okay. Now imagine, so this is average, so you can call it, this is the population mean, the actual population mean. Okay, the actual population, 5 feet and 5 inches. Now you go out and say you measured the, what do you call, heights of say 10 people actually. Okay, you measured the heights of the 10 people and you computed their average, and it turns out their height, their average height is 6 feet. Okay, so maybe you measured the heights of say some people who are playing some kind of a sports, playing say volleyball or something like that. Okay, so the average that you got is 6 feet. So for example, now you increase the sample size, and you say measure the heights of say 50 people, okay, and it turned out that this, this average is really what you call say 5 feet and 8 inches actually. Okay, so you computed, measured the heights of say 100 people, okay, 100 people, and it turns out to be that this average turns out to be say 5 feet and say, I don't know, 3 inches actually. 3 inches. So what does the law of large number is telling you? The strong law of large numbers is telling you, as you will increase the sample size, this sequence of sample averages, okay, this sequence of the sample average will converge, okay, to what do you call this actual average with 100% probability. Here the probabilities are converging, and here the sample averages are converging actually. What do you call to the population average actually, to the population average. Okay, so this is really the essence of the law of large numbers. In both cases, what actually you are saying is that the sample averages converge to the actual average. This is what that we are interested in, that if you make your sample big enough, or you keep on, say for example, making it big, you can say with a pretty much confidence that yes, now the average that you have got from this big sample is really close or extremely close to the actual average of the population actually.